Our lab does a lot with soft robots. Soft robots are, unlike traditional rigid robots, generally made out of soft materials. In our lab's case, we tend to do a lot with silicone bladders, which we inflate to produce different forms of motion, depending on the shape of the silicone bladder and the different fibers that are embedded within it. We think that these robots have the ability to kind of transform the space of robotics because they are flexible, which makes them adaptive to different environments, maybe constrained spaces, or they're also very compliant, which makes them useful in close proximity to humans instead of having to worry about safety factors like will this robot crush the human that it's interacting with. The robot defers to the human or to whatever the object is that's pushing against it. Unfortunately, there are some practical concerns with controlling soft robots because they're flexible and compliant. They are difficult to characterize kinematically. Whereas a normal robot, you can identify the joint angles and you can know the lengths and you can figure out where your robot is in space. A soft robot is flexible and compliant. You can pressurize it to a known location, and then as soon as you have it grab something or as soon as something contacts it, it moves to a new location. So the same things that give it advantages also make it difficult to control. And so we have been looking for soft sensors that we can embed into our soft robots in order to figure out where they are in space. Some of the sensors that we have been using include liquid metal sensors developed by the biologically inspired engineering lab at Harvard. These are liquid metal sensors, liquid metal channels inside of silicone, which are able to sense pressure and linear strain by measuring the change in resistance as the channels are affected by pressure or by stretching. Because they're embedded in silicone, you can put them on a soft robot. They adhere very well. They're thin, so you can layer them, so you can measure both pressure and linear strain at the same time in the same location. So they're very clever sensors, but they do have a couple problems. The liquid metal is difficult to work with. It's expensive to acquire. And any air bubbles or blockages in your silicone channels lead to a non-functional sensor. If you do get a functional sensor, it oxidizes within the matter of weeks or possibly months. So it has a limited life expectancy, and throughout the course of its life, you have to continually recalibrate because your starting resistance has been affected by the oxidation. So we're in search of something that's a little bit easier to use than liquid metal, and so we've turned to optics. We're not the only labs to consider this option. Maybe the slide will change. So the organic robotics lab at Cornell is this over here on the left. They have created some soft silicone waveguides where they basically take light, shine it down a long, thin silicone tube, and measure the light output at the other end, which changes as you bend or pressure or apply pressure or stretch this waveguide. Silicone does not operate the same way that glass fiber optics do. The light does not internally reflect. And so when you do bend your silicone waveguide, you lose a lot of light around bend. So the bionics lab at Carnegie Mellon created a sensor that is surrounded by a gold leaf on the outside. And this was still able to capture capture the bending pressure and extensile strain by monitoring the cracks in the gold layer. As you deform the silicone, the cracks allow light to escape, and they measured that in order to figure out the deformation. We think our method is a little bit simpler, and if the slide will change again, maybe. Here we go. So our method, again, uses silicone as the body of the sensor. We're passing light from one end to the other. And in between, we have optically scattering microspheres. These glass microspheres inside cause the light to be attenuated as you get from the light source to the light receiver. Under normal operation, this is how we would expect it to function. once you apply pressure, we expect all those particles to be compressed together, which increases the light scattering, so you get light attenuation, and you can measure that. When tension is applied, then the distance between the LED and the photodiode increases, therefore you have more area for the light to be lost. Again, you see a decrease in the light on the other side. And then the same for bending, except in this case, you don't have to worry nearly as much about line of sight transmission because the particles will allow the light to be scattered and still hit your photodiode, but you still expect to see light attenuation. So the fabrication, again, if it will change, please. If I ask it nicely, maybe it will. Here we go. I'm going to skip through the fabrication a little bit quickly. I think the most important things to notice are, first we have the LED on one side, the photodiode on the other, some extra pieces of silicone infused fabric at the sides to help with surface adhesion to the end pieces, which are stiff, and the silicone sensor itself is very flexible. So we mixed a couple different sensors and cast them in 3D printed molds. This is an example of the inside of one of our sensors, and we built 3 different kinds. We had one that was completely clear, and then we had another kind that had 2% microspheres by volume. We also made a sensor that was 5% microspheres by volume, but it turned out that scattered the light too much, and even under normal operation, you couldn't really see light at the other side. So we made a second 2% sensor so that we could compare the consistency of the microsphere-laden sensors. So those were the different types of sensors we had. And then for final function, we coated them with opaque black silicone to help protect them from ambient light. To characterize them, we have an instron in our lab. This is a device that we can attach pressure plates to of different sizes. It measures the distance that it moves up and down. It also measures the load. So we use this as our ground truth measurement for 3 different types of pressure plates. And we ramped our load up from 0 newtons to 50 newtons and back down using each of these different pressure plates at a rate of 0.05 millimeters per second. So you can see on this graph the difference between the behavior of the 0% sensors and the 2% microsphere laden sensors. The 2%, well, we'll start with this. The clear sensors definitely have the largest voltage range as pressure is applied, but they don't respond quite as smoothly as the 2% sensors. So on the bottom here, we have the force as it's ramped up from 0 to 50 newtons, according to what is measured by the instron. On the left-hand side, we see the voltage output of the sensors as transformed from the amount of light that the photodiode sees. So the photodiode captured the light, presented it as a voltage. The third thing to notice from this graph is that the 2% sensors were not equal, even though they were manufactured the same way. So we see that there are some production inconsistencies, perhaps with the way that we mix our silicones. And then, as I said, the 5% sensors were too opaque to use. Zooming up on the 2% sensors, we can see the difference in light transmission. Did it change? Good. Okay. So as the pressure was applied across a tighter surface area, we see a more dramatic change in the voltage output. And we wanted to test robustness, so we brought our 2% sensor up to 200 newtons and then back down. These were the same sensors that we used later for these tests. We didn't really observe any damage to the sensors from ramping it up. We thought maybe the glass microspheres would break, but and cause some damage internally, but that did not appear to be the case, at least up to 200 newtons. For further robustness testing, we built additional sensors and ran them through a 1,000 cycle pressure cycle, sorry, 1,000 cycles of pressure cycling from 0 to 35 newtons and back down, and did not observe a change across at least those 1,000 cycles. We also tested linear strain. Again, I will wait for the slides to accommodate. I don't know. Okay. Here again, we use the Instron as our ground truth measurement for the amount of distance that we were stretching our sensor by. And we did a 5-cycle test. Here you can see the clear sensor and then the 2% microsphere laden sensors have a very similar shape. The difference is that the clear sensor starts at a much higher voltage than the 2% sensors. So in this case, we see maybe not so much of a significant difference in the performance. Moving on to bending testing. Again, we used Instron to maneuver our sensor. We added these red beads to be optical markers that we were able to use to characterize the bending using a camera and a vision processing system. Again, moved the sensor at a rate of 0.05 millimeters per second and did this 5 times for our bending test. So here, in this case, you can see the 5% sensor at the bottom and how it stays pretty close to 0. The most interesting part of this graph is that the clear sensors had a much larger range, and so the light got much farther through. The clear sensors started basically at saturation and then went very low down to 0. So we had a much larger voltage range than for our 2% sensors. However, there was a period of nonlinearity when there was a loss of line of sight transmission between the LED and the photodiode. So the 2% sensors had a much smoother curve, in this case also much more similar to each other. And that might be one of the main benefits of using microspheres inside of your silicone waveguide, is for this much smoother curve throughout bending. So if I can conclude, if this will let me change. Our sensor had so we prototyped a sensor with an LED at one end, the photodiode at the other, with optically scattering microspheres in the center. It was robust to 200 newtons of pressure across, and then up to 35 newtons over 1,000 cycles of pressure cycle testing. Can measure pressure, strain, and bending via light attenuation, and has remarkable linearity when it comes to bending. So I'd like to thank my sponsors, and I'd like to open for questions.